Hello, this is my Physics 2211 Lab 5 Choose Your Own Adventure lab report. The purpose of this lab is to observe the motion of a falling spring with a hanging weight. The spring, however, is not ideal as it has mass, and an ideal spring is considered massless. Then I will create a computational model that predicts the motion of the falling spring and weight. Then I will compare the observed motion and the predicted motion to evaluate the accuracy of the model. A brief preview of the results is that the model predicts the motion accurately. The physics principles used in this lab are the spring force, the force of gravity, elastic collisions, and Newton's second law, and the velocity and position update formulas. The formulas for all of the forces and the update formulas are shown in the screen, and the conservation of momentum simply states that the initial momentum, which is given by the mass times the velocity of the masses, must be equal to the final momentum, and that because it is elastic, energy must also be conserved, which is that the kinetic energy must be equal before and after the collision. The following is a diagram for the experiment. Initially, I am grabbing the spring from the top and it is not moving. Then I let go of the top and the top begins to fall down while the bottom remains motionless until finally the spring gets very compressed and it all starts falling. The system includes the spring and the mass, while the surroundings include everything else such as earth, air. Then some key assumptions made are that the only forces are weight and internal spring forces, that motion is purely vertical, and that there is no air resistance. The following video is the observed motion with tracker. An analysis of the observed motion is that at first only the top moves, and the bottom of the spring and the mass don't move. However, once the bottom of the spring and the mass start moving, the spring seems to fall normally. For the computational model, where I model the system, I had to split the spring up into many smaller ideal springs, because the spring is not ideal and its mass cannot be ignored, so our usual formulas are not accurate. Then each of the little springs connecting the little masses is an ideal massless spring, and all of the mass is contained inside of the n masses. The mass at the top is considered to be the mass 0, and the mass at the bottom is considered to be the mass n-1, as in total there are n masses. The image on the right is what is shown in the GlowScript model. For the initial conditions, the system must be in static equilibrium, and for this to be the case, each spring must support the weight of all the masses below it. Therefore, for the ith spring, the force it exerts on the mass below must be equal to all of the weight below the spring, which is given by n minus I times the mass of the spring over n plus the mass of the hanging mass times g. And if we solve for the magnitude of L, which is the length of the spring, how stretched it is, we get that it is what is being shown on the screen. For the computational model, at first I have to calculate the net force on each of the masses as well as the hanging mass. For this, for each mass, I iterate over each of the masses, and first I calculate the weight force on each of the masses, which is simply given by 0, and then minus the mass of each little mass times g and 0, and then to calculate the force on the top, as long as the mass is not the topmost, and that is given by the if I greater than 0 condition, I simply calculate the force being done by the spring on the top. Then I calculate the force being done by the spring below the mass, and if we are on the lowermost mass, which is given in the else condition, the spring below must use the hanging mass, as there is no other of the small little masses below it. Then I have to calculate the net force in the hanging mass, which simply does the same procedure, but only calculates its weight and the force being held on it by the spring on the top. Then, using the position and velocity update formulas, I update all of the positions and velocities of all of the masses as well as the hanging mass. The following is the result of the computational model. The graph below shows the predicted and the observed motion of the top and the bottom of the spring. As we can see, the model quite accurately is predicting the real observed motion, except for the topmost part of the spring at the moment it gets to the maximum amount of compression. Nevertheless, for such a complex system, the prediction is still quite accurate. Some sources of error include not including air resistance, and that very compressed springs may not have linear forces. There could also be better ways of simulating the real spring. Then the additional questions are: what if we remove the hanging mass, in which case the initial spring would be less stretched as each spring has less mass to support, and the position of the center of mass would change. However, its displacement would still be the same. And what does it mean? It highlights the importance of taking everything into account in the computational model, because a simple model that models the spring as a single stiff object would be inaccurate as the top and the bottom do not move equally.